Writing is quite bad, but I double check that I am audible. Who's online? Azan, can you hear me? Yeah, I think it works. Okay. So the second quick announcement. Yeah, I can keep the announcement for later. Okay, so that's the logistics. So we have, okay, it's not really an announcement, but debriefing, or I guess looking at assignment 3 to see where the hiccups were. I know one of the hiccups was about, is it you that I've been emailing back and forth? Okay, one of the hiccups was with respect to vocab size. So one of the ways, if you're not able to iterate, and if you need to control batch sizes and whatnot to put things into memory, first of all, the vocabulary size, I don't know what it is, maybe 60,000. So you could actually trim the vocab size by saying, okay, some words I'm going to by default put it into a default token, which could be like irrelevant word, for example. So you could kind of control the vocab size from 60,000 to maybe even 10,000. You can drop a lot of words. Actually, you should probably drop the more frequent ones because they're not that informative, perhaps. But anyway, so there's some choice you can make. So vocab size is definitely something you can control. And the second thing is, even if there's a large vocab size, which kind of influences the number of probabilities you need to output at every, whether you're doing sentiment classification or this language modeling, you can also control the embedding size. That's one of the bigger, I guess, matrices also. I think you've controlled that in your previous assignment when you had the matrix embeddings, the movie embeddings. Good chunk of you chose a small embedding size anyway, like 3, 5, or 10 or something. So that's also something you can control to make your model a little bit smaller so that you can actually train. But yeah, batch size would be the obvious thing to also control if you're not able to, you're hitting out of memory errors. So there are a lot of things to control, but the problem is if you kind of reduce these things, then you will increase the number of iterations, or kind of training will be slow, or maybe very noisy and things like that. So there is pros and cons. That's why there's a lot of demand today, I guess, over the past year for this specialized hardware, and in fact, the state-of-the-art hardware has like 40 or 80 GB probably VRAM. So it's very, that is quite a bit. But even that is not enough sometimes. Actually, it's become common to have multi GPU setups and doing what is called, I guess, model parallelism and data parallelism, where you could split multiple layers across multiple separate GPUs and separate computers, and then kind of forward pass through multiple GPUs and backward, backdrop through multiple GPUs and so on. But we'll not get into those technical details, I think, since we are just ramping up. The objective of this course, actually, not the course, but each lecture is mostly to introduce the canonical model. And so today is actually very relevant in that sense. We're going to look at a canonical model for all the new LLMs that you're seeing. So the canonical model is just a transformer architecture. We'll mostly be discussing it in the context of translation. So translation is something that you worked on in assignment 3. So in the context of translation, we'll look at the canonical model, which powers much of the stuff that's seeing in 2023. The model was proposed in fall 2017. So it's been, 2024. So it's been 7 years, 6.5 years. A lot of innovation has happened over the years, but we'll look at the 2017, 2018 version of that base model. This is a base layer, like a CNN layer, so con layer. Anyway, that's where we are. So coming back to assignment 3, since the number of students is very few, we will see if we want to kind of revisit this, like jump into code and stuff next time. Okay. But I hope that gave you a sense of, a lot of things, moving parts. So data import part for vision was a little bit different, mostly kind of dealing with the transforms part. normalizing, doing data augmentation, and then mostly just defining the data loader and the data set objects correctly. Here, there's the additional thing of tokenizing, basically encoding your words or whatever is the representation to an index, basically, so that you keep a vocab, so that you can go back to an index to a word or word to an index, so that you can actually get the embedding for the word when you're doing your sequence modeling. Okay, so there's extra, which is extra steps that you did not see, I guess, in the vision situation. So I hope through the friction of trying to do this, you get a sense of, okay, this is like, it's not complicated, but one time you see it, then you can start thinking about optimizations and the impact of those pre-processing steps on the model. For example, tokenization is actually a huge concept. And there are a lot of interesting approaches to tokenize data. Like, you don't have to tokenize at the level of a word. You don't have to remove the special characters, or so you can do many things of how to kind of get to the right number of tokens. And if you see many of the machine learning models available today, LLMs specifically, they're all, especially if you use a proprietary service, they all charge by number of tokens. So what are these tokens? Are basically like words, maybe even subwords, but how do they map these words or subwords to numbers is a interesting, it's a modular problem in itself, in addition to training and defining the model and all that. Okay. You did some rudimentary tokenization anyway in assignment 3, but I'm just mentioning that that's a important aspect. But we'll get into the code for this perhaps next time, because we'll look at some example code for transformer models towards the end, or maybe next time. So we'll look at kind of their similar code, just the model definition will be different. So we'll look at that next time. So I took some time to explain, but what is the objective for today is to really get started with what, it's titled Advanced NLP, but it's mostly just talking about, okay, we want to do sequence modeling. We want to do all these cool applications like translation and other things that you have seen, but we want to make use of the more modern architecture out there, which is the most predominant one right now. There are other competing architectures though, which is called the transformer architecture. So we'll look at the transformer architecture. It's not just for translation and not just for sequence modeling. It can be used for many things. But that's the goal for today. As a part of transformer architecture, there's going to be a notion called attention. In particular, it's called self-attention. We will kind of understand what is self-attention, which is actually a central concept for when defining the transformer architecture. Just like when we're talking about CNNs, the central concept was how does the convolutions happen, and how are they kind of taking advantage of parameter, reduction in parameter? How does the reduction in parameters happen, right? The same thing for transformers. We'll look at attention as a core component. But before that, we'll look at, so as a precursor to that, we'll look at something we left off last time when we were looking at RNNs. There's also another concept of attention called encoder-decoder attention, which is something, I think it was already implemented in one of the reference codes that you guys use in the assignment, but we'll talk about it here. Okay, so that's the goal. So the goal is to really kind of revisit the precursor, which is not listed here, but it's called the encoder-decoder attention. Actually, it says here. So I call it simpler attention mechanism, but it says it's a concept. So we'll kind of appreciate what that concept is for RNNs, which is the encoder-decoder architecture that we've seen, and then talk about what is the self-attention concept in transformer architecture. Okay, and then in the transformer architecture, there's going to be some new vocabulary introduced, which is notion of keys, values, and queries. It's just a terminology for some vectors. Okay, vectors and matrices. So we'll look at what these vectors and matrices are, why they're called that way. And if time permits, we're going to look at one popular, used to be popular, it's still popular, a model called BERT, which is a canonical example of doing contextual embedding. Okay, so word2vec, which we saw not last lecture, but the lecture before that, is an example of it's very good. It's something you should use, and you have to use it, not word2vec perhaps, but Glow and FastText and so on. But they are very good embedding models, pre-trained models, but they're static embeddings. So for the same word, it's always going to be the same vector. So for the word university, it's going to be always the same vector. whereas this slightly newer generation models, they are explicit neural networks, and so they will give a slightly different vector for the same word depending on the context, depending on the sentence. Okay, so they're still used as pre-trained models for generating contextual vectors, which can be used for whatever downstream application. So we'll look at that non-static version of going from words to vectors in towards the end of this lecture. Okay, so that's the goal. So to appreciate encoder-decoder attention, self-attention, and some extra vocabulary like keys, queries, and values, and then finally this notion of stepping away or kind of getting the next generation of pre-trained NLP models. Okay, so with that, let's actually jump into our slide deck. So the same content is actually there in the, slightly different visualization is there in the new slide deck. So this is slide deck 5A, but the slide deck number 6 also has the same content. So I thought, let me prefer one which is a little bit different animation than the other one. Okay, so but they both are the same. In the initial few slides of slide 6, you have the same content, and we'll actually get to slide 6 in a second. So what are we trying to do, right? So just to recap, where we left off last time is actually towards the end. Let me just go over here. Let me just show an example. I don't think I have it here, but we were looking at some architecture like this, okay, auto reply or translation, or the example that the assignment question that you worked on, translation, right? So there was a bunch of encoding steps, and then there's a bunch of decoding steps that you need to define in your model. So there's going to be an encoder, potentially an encoder object or encoder model specification, and a decoder model specification. And so what we're trying to do is kind of enhance that encoder-decoder architecture. So previously, we were like, okay, compute all the hidden vectors, but only use the last one and then generate the first response, feed it back, generate the next response, and so on. Right? That was the forward pass, right? And an improvement over that is what we're looking for. Okay, so what is that improvement? Is the notion of trying to use all the other hidden vectors that we computed also to potentially generate each one of my decoded responses. So if my decoded response is has 4 words, let's say, so therefore I'm doing 4 iterations. Every iteration, what I want to do is not just rely on the input to that RNN block, which is just the hidden vector, or is the final hidden vector of the encoder side, but I also want to look at potentially the other hidden vectors that are there. Okay, so that's the extra optionality that I want to enable. And how am I going to enable it? By just having at the end of the day, it's all going to be a definition of extra wiring in the neural network, some extra connections, some extra computations that are going to happen. Okay, so we'll see that through an example, and we'll stick to the machine translation example because auto reply and machine translation, they're all kind of similar, and you've worked on machine translation assignment 3. So let's actually do that. So what we'll do is, again, just think of the forward pass. That's what we're doing. Okay, there are many ways to introduce the same concept, but first I think it's always good to say, okay, what is mechanically happening for a small illustrative example? So what are we trying to do, right? So again, so this one is an example for translation. So we're going from French sentence to English sentence. And let's say we have this French sentence, and we have the red, these 4-dimensional vectors represent the hidden vectors, okay, that we computed while we were encoding it using RNN or LSTM block, okay? So each step is just an LSTM cell producing the hidden vector, and then it's being used along with the new input to produce another vector, and so on. Okay, so this red part should be clear, okay, and this arrow should be clear. Now we want to start decoding. Okay, we want to give a special token, generally like a dummy token or a start token, and then we want to start producing a response. We're just doing forward pass, no training here. Okay, we can think about training later. To do that forward pass, so previously without attention, you would just create some. So you take the final hidden vector, take the embedding of the special token, like the start token, and then just apply it on an RNN block, so RNN cell, sorry, and then you just get a hidden vector, and then you could just transform it back to the 60,000 dimensional vocab size, and then get a word directly, right? So instead, what we're going to do is apply this attention computation, okay, And again, the goal is to kind of focus on other hidden vectors whenever needed. Okay, so maybe the first word generation depends on maybe the hidden vector, which is at the, which was the first hidden vector. Okay, that is what we're trying to enable. So what is the mechanical computation here? It's the following, right? So once we generate the hidden vector here, the green vector, then what we're going to do is we're going to start basically combining this hidden vector with each of the previous 4 hidden vectors in this example. So whatever the sentence length, those many hidden vectors, I'm going to start composing my current hidden vector, okay, to eventually generate the distribution over words. I don't want to directly go from this green vector to the distribution over words through a linear transformation, perhaps, but I'm going to do this intermediate computation, which is let's call this S1 for the decoded hidden state. And let's call this H1, H2, H3, H4. So what I'm going to do is first compute a score, a simple number using H1 and S1. Okay, H1 is this red one, the most leftmost vector. This 4-dimensional vector is called H1. The rightmost vector currently is called S1. And I'm going to compose them together. Compose just means like use them both together. For instance, this F could be just an inner product between H1 and S1. Okay, you can just say H1 transpose S1, that's my number. And that we're going to call it as attention score. Okay, that's what is the number supposed to signify? That number is supposed to signify how important this hidden vector is for my current output generation. Okay, right now there are no parameters, so you may say, okay, how is it kind of going to signify that? We will see that. We'll add the interpretation in a second. So that's the attention score. And similarly, we're going to just repeat that computation again and again and again 3 more times, because we have 3 more hidden vectors, right? So let's compute the second hidden attention score. So this vector, again, composes this vector, produces the second score, which is in the blue dot. Okay. Similarly, third one and fourth one. Now, what do we have? We have 4 attention scores. Okay, 4 numbers. Because why 4? Because the input we had 4 hidden vectors. Okay. Next, what we're going to do is actually normalize it. How do we normalize? You know how to normalize scores. Given a bunch of scores, you know how to do a softmax transformation. So that's exactly what we'll do. So we'll normalize it, and that's going to lead to this type of a distribution, a probability mass function. Okay. And from here, this is the first time I'm showing some magnitudes. And from here, the interpretation in this illustrated example is that perhaps we want to kind of say that this hidden vector is more important while decoding at this first step than perhaps the other 3. Okay, that's the type of interpretation I want to bring in. Okay. So how do we, if we think that that is the case, that the first hidden vector, the leftmost one, is actually important, then what are we going to do? We just want to kind of use it, right? If it is important, then we want to use it while decoding the first word. How are you going to use it? There's a very simple and natural idea here, which is to just use this probability mass function to average these hidden vectors. Okay, these 4 hidden vectors, I'm just going to average, but I'm going to do a weighted average. Because the weight for the first one is high, that one would be the predominant one in that weighted average. Okay, so let's do that. Yeah, as I said, we're going to focus on the first hidden state. Let's do a weighted average. That weighted average is called the attention output. Okay, so this is the simple computation that's happening. It's a very mechanical process where whatever hidden vectors you have, the first decoder hidden state that you have, you're just going to compose it as in you could do inner product or whatever, get these attention scores, normalize it, you get the attention weights, and then you just do a weighted average, okay, to get an attention output. The Z1 is just a weighted average, okay, where the alphas were the ones that we computed by this composing each hidden vector with the decoder hidden vector. Okay, so what is the net result of this attention output, right? The attention output is basically containing information about every hidden state, but it depends. It is predominantly it's predominantly capturing that hidden vector which has the highest attention weight, right? So let's call this again another vector here. It's still in red. That's Z1. Now, once we have this, then the next few steps at decoding steps are exactly the same as before, except we're going to just concatenate this vector with this current RNN cell decoder hidden state, just concatenate, and then exactly do the same transformation that you were going to do before. Like, for example, if you're just going to map these, as in bring this back to the vocab size dimension, then you just have to concatenate them together and then apply an appropriate W matrix, which goes from that, maybe 8-dimensional vector to 60,000 dimensional vector. There's a 60,000 dimensional bunch of scores. Okay, that's the idea. So use these two, perhaps concatenate. This is what I'm showing here. Z concatenated with S. So that's why it's two times the original dimension. And then just to apply a transformation G, which would be just a linear transformation, and then apply a softmax to get the distribution over your vocabulary. And this is going to be on the English side. So maybe perhaps from there you sample a word, or you take the argmax probability and then pick the word with the highest probability, and that's the word. And then the decoding process is the same as before. You use the word HE, input it as the second step of decoding process, and then you get the second vector, right? The second vector exactly follows the same process as before. So we do this composition with each of the 4 hidden vectors. This time the weights are such that perhaps the second word and the fourth word seem to be important to decode at this point. And how did these importance come about? It's just by training. The attention mechanism is part of the training. And so now it learns to appropriately make use of the hidden vectors as needed. Okay. Because previously there was no such way to kind of rely on previous hidden vectors. The only way was the previous hidden vectors were kind of going through the RNN cells, getting transformed, and that's the only way the information is propagating. This time, information can propagate by just doing a weighted combination like this, and that can influence the output. That's all we are enabling. We are enabling it's like the ResNet model where there was the residual pathway. So it's very similar to that, okay, in terms of wiring up a neural network. So the same idea. The length of the output is very different from the length of the input, but you can see, right? So any questions here with attention mechanism? So this is called encoder-decoder attention mechanism. So when we're decoding one step at a time, we're trying to attend to the appropriate input by doing, by basically composing with the hidden vectors of the input one at a time.
In terms of like the operation to say, so I don't know, it was back when you had like the earlier screen, so we have like the word we're on and then maybe 4 words ago.
Yeah.
So that's just something in terms of the operation, you said it's just gonna be like a linear combination of the two.
Yeah.
But so that's just something that we specify and just kind of, by testing different configurations of a model, figure out what's best.
Sorry, which one are you referring to? Are you talking about the function which composes
the function to create like the blue bars?
Oh, the blue dots, and then the bars are just the softmax version of it. Okay. But the blue dots are the scores, which were actually equal to some function of the hidden vector and the encoder side hidden vector and the decoder side hidden vector. Yeah, that function will see some examples, but you get to choose some. And before that, I want to not get the machine off. So let me just plug this in. Okay. I mean, it's the same idea is written in a for loop. So for every time step of decoding, you compute the decoder hidden state. For every encoder hidden state that's present, so T length 4 in the previous example, compute the attention scores, which is this function is the only thing that I have not disambiguated yet. I just said you can just use any product, but there are a couple of other choices that we'll see in the next slide. But once you get attention scores, get the attention distribution, attention weights basically, which is just a softmax of that vector. You get a probability mass function, and then just apply a weighted average of the hidden vectors to get the weighted encoder state. And that's just concatenated with the decoder hidden state, and then you can do exactly what you're doing before. So this is an extra piece of information that's coming in. Okay. Yeah. So here are some examples of functions, right? One of the functions is just S transpose H, which is what we just discussed. If they are the same dimension, then this is it doesn't have any parameters, but that's one way to do it. But the couple of other versions are multiplicative attention, where you do the exact same thing, but you have introduce an extra W matrix in between. So now you have to learn how each coordinate interacts with each other, other coordinates. You're basically doing a weighted, some weighting of while each coordinate interacts with the other coordinates. And you can also ensure that the dimensionality of the decoder side doesn't have to be the same as the dimensionality of the encoder side. Okay, so you could choose a different hidden vector size on both sides. And finally, you can have nonlinearity also, where you are individually like transforming H vector and S vector into some new same dimensional vector space, adding them up, and then applying another parametric transformation. So these are just functions. I mean, you can use any functions, any parametric function, but the moment you introduce parameters, those will also be backdropped and learned. Okay. So these are just to show like what types of attentions you can have. Yeah. So now coming back to that example, it's just showing the same thing that we saw, but for the auto reply example that we had in the previous slide deck. So this one, okay, this one not yet attention. I think, yeah, you could look at I said in the previous in the encoder side, but instead we can create inner product with previous states. So this is the same A's there. And then you can do a scaled version of it, which is the softmax version, which is the B's. And then you can sum them up, which is the weighted averaging. And then you can use that and the hidden vector to create the final word. So this is just the same illustration as before. So let me not spend too much time on that. But yeah, but this attention mechanism, although I have shown it in the context of a translation setting, which is a variable length input and a variable length output, you could actually add this attention even when you're doing sentence classification, even when you're doing sentiment analysis. You can say that, I went through the sentence, input sentence, which is variable length, but I don't have to use the last hidden vector to only say, okay, whether it's a positive sentiment or not, right? It's one step beyond just using the last hidden vector. You can just say, oh, I will concatenate all the hidden vectors together. But the only problem is that concatenation depends on the input length. If the review is like of 5 words, then you'll only have 5 times hidden vector. If your review is 10 words, then you'll have 10 times the hidden vector. So there's an incompatibility there. And this is one way to kind of get around it. You're basically doing a weighted averaging of those hidden vectors, right? So a more naive idea could be that while making the final sentiment prediction, you can just say, oh, I don't want to rely on the last hidden vector. I'm just going to do a uniform averaging, like I'm going to take a H1 plus H2 plus H3 plus H4 and divide by whatever the number of words, and that's going to predict. Okay, that's a simple version where you're not thinking about attention weights and attention scores and all that. But the attention weights and scores do help, and that's why it's part of the definition of an encoder-decoder attention. Okay. So this is where I think innovation comes in, and this is what you wouldn't know beforehand, like whether this type of a thing would help. I mean, you have some intuition of, okay, maybe I should use the hidden vectors that are kind of not being used while decoding. And how do I use it? I can do some weighted averaging. I can do some just regular averaging. So that part, once you know the intuition roughly that you do want to use the hidden vectors, then how to use it? This is one version where you can just use based on, you can use it based on this type of a composition. So once you have an intuition of, okay, maybe some information can be used, this is one example of a thing that people have kind of figured out. So all these architectures, they seem like very hard to grok, like at the first instance, that, oh, why did they come up with this? But roughly it goes, it's basically motivated by some empirical observation or some motivation of you want to incorporate information and things like that. Okay. Same thing with LSTM. Although we had a narrative about LSTM's different functionality, cell states, forgetting, and remembering, and all that, they did want to have that type of interpretation or motivation, and then they built the gates and so on to kind of capture that. Okay, and it worked well. Any questions about encoder decoder attention? No. Is it too complicated or reasonably okay?
Reasonably okay.
Okay. Yeah, I mean, the first time you see it, it's not complex. It's straightforward, but it does, we are following the previous lecture. So if you haven't followed the sequence models, then it's gonna be like unclear what's happening. But as I said, one of the goals was to appreciate encoder decoder attention, and the motivation was exactly this: that we want to use hidden vectors more judiciously. Now, the central point of this lecture is really the transformer architecture, and within that, there's also self-attention. So there's also an attention mechanism. Okay, that's what we want to spend for the remaining like an hour and a half that we have. Okay, so in this deck, we do have actually a recap of the attention in sequence models. There's a different animation, but it's kind of the same idea. So I will skip that, skip few slides there. So the layout for today's session is as follows. First, we're gonna again appreciate the forward pass, and we'll kind of do it slow so that it's kind of clear what is happening, just like we did for CNNs, as well as LSTMs and so on. So bulk of the time we'll try to spend on this. What is the architecture? Although we'll talk in the context of a specific application. The moment we have sequence models, there are many applications. The application that we will look at is exactly what we've been doing so far, which is translation. Okay. But within the translation application, we'll talk about the new architectural element that we're going to define, which is the transformer layer. Okay. Which will have transform blocks and some details related to that. In particular, we'll look at one detail called self-attention. Okay. As time permits, we're going to talk about this transfer learning idea, which we saw for CNNs, right? So CNNs, and in fact, you guys did a lot of work in assignment 2 on that. So we look at transfer learning idea beyond just using a static word embedding, which is what you did in assignment 3. How do we go beyond static word embeddings? And that's the idea of transfer learning. Although we'll kind of see it in the context of a specific application, and this time it's going to be simple sentiment classification or simple sentence classification. Okay, so IMDb data, exactly what you've done before, but we'll just see how to use a pre-trained model. And maybe this lecture, early next lecture, we'll talk about some variations of this architecture. Okay, so the variations are mostly because of different applications. So we'll look at them perhaps at the end. So okay, so we'll skip the illustration, but I just want to recap what does attention mean, because there's going to be another notion of self-attention that we'll see in a few slides, but the motivation is still the same. Like, what is the intention of the designer who designed these models, the designers who designed these models, is to basically attend to parts of the input, parts of the other intermediate computations as needed while I'm generating my output. That's basically it. It's as good as saying, okay, if I had other parts of my computation going on, how can I also use it while kind of generating my output? Okay, that's the core idea, and we saw exactly this, right? So how can I attend to some parts, as in focus on some parts while generating my output? In this case, while we were decoding, we were attending to some parts of the input, basically, right? That's where the word comes from. Just means that the prediction of the current output depends on specific parts of the input sequence. So you're attending to something. Okay. So the illustration I'll skip because it's same translation idea. So yeah. So it's the same translation, but now let's look at a couple of like attention weights themselves. Like, how would they look like? Okay, so in this case, again, French to English translation, and it's a different input and a different output than the illustration we saw. But here we're just saying, if we had these 3 hidden states, since we had 3 words in the input, then each output that I'm decoding 1 word at a time. So let's say I decoded 4 words. Then for each word, I would have had attention weights, right? So for each word while decoding, I would have alpha 1, 2, 3, 1, 2, 3 in this case. Those alphas are here. Okay, so this is just the 3-dimensional vector of attention weights for each decoded output. Okay, so you can see here that for this sentence, it turns out that while producing the first word, just need to focus on the first word of the input also. Okay. And similarly, when I'm producing the last word, I just need to look at the last word also. Okay. But you can imagine sentence pairs where the words positions could be completely different, and then you'll see a different pattern. So here it will mostly be attention would be mostly like near diagonal, if you want to call it that. So as you're decoding, as you're decoding one word at a time, you'll kind of attending one word at a time. Also, the attention weights kind of progressively move as well. Okay. But here's an example in the next slide where you can see the clear effect of you might have to attend in a different way. For example, you can see that this French sentence, when we are decoding, then while decoding the word European, we actually did not attend to the zone word, right? So we knew that we had to actually attend to the appropriate word to decode this one as European. So what I'm trying to say is that you don't have to have attention weights kind of peaking at the diagonal or near diagonal area. And first of all, this doesn't have to be even a square, right? So the number of words or tokens on in the rows is not the same as the number of tokens on the columns. So if you think of a rectangular matrix, all I'm saying is you don't have to have attention exactly like progressing in a linear fashion. Okay, so it could be like off diagonal, like it's a reverse. It could be a reverse like this, or it could be all over the place depending on how the words have to be arranged depending on the grammar.
It might also be this shape.
Yeah, it can be any direction. The shape can be anything. It depends on the sentence, the language. Yes, exactly. Yeah. So this is just a visualization. So this is a useful visualization. So if you have already trained a model with attention and you want to kind of understand, is the attention even helping, you could probably have some canonical input output pairs for which you're trying to see is the attention actually like capturing appropriately, like focusing on parts of the input, right? For example, like if you had an attention which was equally across all words for every output, then maybe you don't need to have attention because it's like you're not attending to anything. Or sometimes attention will say, okay, maybe on the last hidden vector is enough to kind of me to decode next three outputs. Then you will be able to see that. So it's a good post diagnosis tool. Also, kind of adds to interpretability a little bit. Okay, obviously you can't interpret the hidden vectors themselves, but you can interpret the weights in this example, for example. Yeah. So some amount of interpretability, and this is actually a good tool. Just like we had some interpretability or diagnostics of CNNs, this is an example diagnostic tool that you can use, except that it's not really scalable in the sense you have to take an example and then look at the attention weight to kind of get a feel for whether whether attention is helping or not, right? Okay, so those two were just kind of complementing the previous deck as well. So now let's actually get into transformer architecture. So, okay, so what is this model, right? So this is a model that's, I mean, I don't want to justify it more and more, but this is a model that's used for most modern generation large language models and other models, many other models in the deep learning world or the machine learning world today, both commercial and research. It's a model from 2017, and it can also be used for sequence modeling. That's the kind of at least initial motivation. But as you saw, right, sequence models can also be used for fixed length models also. I mean, there's nothing preventing you from using sequence models for fixed input length model settings. Attention, it's the same idea as before. Same idea as the encoder decoder attention in terms of motivation, but a slightly different take because for some reasons that we'll see in the next few slides. So let's again stick with neural machine translation. So the translation application, it's called neural machine translation. Machine translation is a very classical name for this type of problem. And if you use neural networks in there, it's neural machine translation. Okay. So what do we want to do? So what are we going to do is go from a very high level view of what the situation, what the solution could look like, and then keep opening the boxes. In this case, the pink box and the green box will open them and kind of understand how the forward pass happens. Okay. just like we did with LSTM or a CNN. We want to kind of understand the forward pass because backprop is something mechanical, and we'll kind of offload that complexity to PyTorch or TensorFlow or something, right? So what do we want to do? We have this French sentence in this architecture, just like the RNN architecture. And so I will say that if you're getting confused, forget about the RNN architecture and just focus on how this architecture is laid out. It looks like the RNN architecture with at least the similarity is there's going to be an encoding part and then there's going to be a decoding part. And that's only because we are looking at translation application. The transformer block itself has nothing to do with whether there's an encoder or decoder. But there is an encoder decoder in this version of a machine translation context, the setup of the model. Okay. But this is where the similarities between RNNs and transformer architecture is going to end for this application. So what is happening is that there's going to be a bunch of encoders. These are not LSTM cells. So you kind of forget the LSTM and RNN stuff. There's going to be a bunch of encoders and a bunch of decoders. Okay, we're going to open them up. So what did we do from previous slide? This slide is just, okay, if this is the green box, we just open it and we have now 6 sub boxes, right? Subcomponents. And similarly, we have just in this illustration, we have another 6 subcomponents, which are the decoder blocks. Now, first of all, note that the sentence length is 3, just 3 words, basically. But the number of encoders is 6. So that means that the number of encoders has nothing to do with the sentence length. Sentence length could be 10 words or 20 words, but the number of encoder units is going to be the same. Okay. It's going to be some fixed predetermined choice when you're defining the model. Similarly, decoder side, there'll be some fixed number of decoders. Okay. The encoder-decoder part, which is this bold-faced arrow, is just representing that, okay, if I have some sentence, there's going to be some computation going on the vectors related to those words of the input sentence, some computation on and on and on, perhaps 6 times. Seems like 6 similar type of computations happen. And then whatever outputs there are, mostly these artifacts are going to be essentially vectors. Those vectors will be used in the next process, which is the decoding step. Okay, so we'll look at how are those vectors explicitly used and all that in the next few slides. But that's the process. So all I want to focus here is that the number of encoder units has nothing to do with the sentence length, which was in your RNN case, the sentence determined how many times your RNN was called, RNN cell was called. Okay. Any questions here? Okay. So now we're going to zoom into that one green block. Okay. So because all the 6 green blocks, it's all the same. Let's look at one of them. So the key element of this transformer architecture is going to be that there's going to be parallel treatment of all input elements. Okay. So for this illustration, for the next few slides, we're going to focus on the first encoder block, mostly because at the first encoder block, the inputs are going to be the words themselves. But if there were second encoder block and third encoder block, there'll be some inputs, but they're mostly going to be vector representations. But the number of such vectors will be exactly the same as the number of words. Okay, and in particular, there's going to be parallel treatment of each of the words together. So if there are 3 words in my sentence, all of them are getting parallelly processed together. Okay, it's not really parallel processing. It's just that all of them are simultaneously being acted upon. Like if there are multiplications happening, each of the embeddings are being used together while some multiplications are happening. Okay. And so this green box has 2 subcomponents. One of the components, which is going to be new and it's a core idea, is the notion of self-attention. Okay, and the second component is just a feed-forward neural network, which we have seen many times. So let's actually get into the self-attention block. So what is happening in these arrows here? So I think this arrow you can ignore for now because this only makes sense. This only makes sense as the last encoder, and in fact, it is no different arrow. It's the same as this. So ignore the right arrow here. What are these arrows? These are just since we are doing parallel treatment of my 3 words or 2 words or whatever my illustration is. So these arrows just correspond to those vectors. Okay. If there are 3 vectors, 2 vectors, depends on the sentence length, or 10 vectors. Okay. So let's actually remark a couple of more points before we get into opening up these subcomponents also, feed forward as well as self-attention. We'll open them up so that it's very clear what the forward pass is at the encoder block level. Before that, I just want to point out that a couple of remarks that first of all, encoder units don't share weights. This is just to contrast with RNN, because in RNN case, it's the same RNN unit being applied again and again and again. In this case, each of those green boxes have their own parameters. Okay. As I said, there are the two sub-layers or subcomponents. One is a self-attention component, and the second one is a feed-forward layer or component. All words, all vectors are input at the same time. Okay. The feed-forward layers weights are reused across words, which is a detail that I'll talk about later. And it turns out that the decoder unit, so this arrow here, as I said, it only makes sense at the last encoder when you actually have to pass information to the decoder side for this application. So don't worry too much about this arrow in the center. But the decoder block has exactly the same kind of setup as the encoder side, except there's one extra layer, sub-layer in between, which is the encoder-decoder attention, okay, which is what we've seen before, but it's not clear how that fits into that block there. We will talk about it later. Okay. So for now, the simplest way to approach is really understand how am I going from, let's say, a bunch of vectors here to create a bunch of vectors there. Okay, that's really the core of the operation, so we want to understand that. Okay. In particular, we want to understand this step because feed-forward is clear, like it's just a vector matrix times a vector plus some bias and just push it out, right? So that's clear. What is not clear is what does self-attention do? And the idea is helps transform inputs, input vectors, input word embeddings, while taking other inputs, other word embeddings or other words basically into consideration. That's what self-attention is. Okay, it's nothing complex to nothing too complicated. It's just that when I'm as I said, we're acting on each of the words or each of the words related vectors, together. When I'm acting on the first word, I want to kind of use information related to the other words while transforming some vector, doing some matrix operation on the first word's vector. Okay, so here's the really, now that we are really looking into the encoder block, let's say we're looking at the first encoder block. Okay, so just for simplicity, because that way you can actually interpret that, okay, the first word is literally there's a word here. So this word, and this word. Let's say they have we use word2vec or not word2vec in this case, fast text, let's say, to get a French vector embedding for this word, these three words. Okay. And then we want to pass each of these words into the self-attention sublayer. And each of these words will produce a vector, let's call it Z1, Z2, Z3, right after the self-attention block. Okay, so self-attention sublayer is going to produce one vector per word, okay, in parallel. And then each of those vectors goes through a feed-forward layer and is also going to produce another vector. We haven't given a name here, but let's call it R or something, R1, R2, R3. So that means for 3 words, I'm going to get 3 vectors. But what if my sentence length is going to be 5? I'll get 5 vectors. So how can I predetermine a block which can work with both 3-word sentences and 5-word sentences? And the simple answer is you just assume a max length. Okay, and this is actually kind of relevant to this idea of how many tokens or how many words or what is the longest sentence I can process. Okay, so in RNN case, if you had a really long sentence or a really long review, or maybe a review of the paragraph, you can actually just keep calling the RNN cell, whatever, like 100 times. Okay. It may not be effective, perhaps, or it may be effective, but you can call it 100 times. Here, you do have to kind of say my sentence or whatever variable length input has a max size, okay, max context size. For example, it could be 20 or maybe 100 or whatever. So we'll see some pre-trained models what their choices are, but something you have to choose beforehand. And if the sentences are smaller, that's okay, because the other numbers, other words, there are no words, you can just say dummy words or no words, so basically zeros. You can work with zeros there. Okay. And second thing is embedding size. Obviously, you have some embedding size you need to choose all the time. So let's say it's something 512. Okay. if the first layer, obviously you'll take the word embeddings. If it's the, if the second encoder unit or the third encoder unit or the sixth encoder unit, you're going to take the inputs are going to be not the word embeddings, obviously, but some outputs of the previous encoder unit. Okay, that's fine. Any questions here in terms of, it's very block level, somewhat boring, but kind of it's good to remember that. Okay, so we are actually, I'll stick with this illustration for the next 2-3 slides, but in this illustration, I only have 2 words. Okay, I want to kind of reduce it to a really the smallest example where I can show what self-attention does. So here's the 2 words. In fact, we dropped the French part and we just said, okay, thinking machines is the input. Okay. For these 2 words, what do we want is x1 and x2 are the embeddings, inputs to the encoder unit, and z1 and z2 are the intermediate outputs, which lead to r1 and r2 as the final outputs of this encoder unit. Okay. So this encoder unit has a feed-forward part, which is a little bit clear, like z1 just getting transformed to r1 is like not complicated. But the question is, how do I get from x1 to z1? Okay. As I said, self-attention, the whole point is that when I'm going from x1 to z1, I should also rely on x2. And similarly, when I'm going from x2 to z2, I should also rely on x1. Okay. Very similar to the decoding idea. When I'm decoding, and the decoder of the encoder-decoder architecture for LSTMs, I said while decoding, I want to kind of use the hidden vectors that were already produced. Similarly, when I'm trying to compute something like z1 from x1, I don't want to just use x1 to z1, but I also use something else. Okay, that's the similarity between self-attention and encoder-decoder attention. Okay, so let's actually now look at really this brown block here. What does it do? So there was an interpretation, right? So when we did the encoder-decoder attention, we saw like a diagonal, like a matrix or rectangular matrix where there was weights on which part of the hidden input influenced the output decoding. This is just trying to show, this is forget what the name of the tool is. There's a link. This is not the link, but there's a different, I think it's called LSTM Viz, I believe. I can share it offline or link it on the course repository. It just shows what attention means, right? So here it's saying the animal didn't cross the street because it was too tired. We are trying to go from vectors to vectors for each word. Okay, so for every word, we're going to go from a vector to a vector. So what we're trying to do is that, let's say the vector for it, okay, there was some vector, and we're going to create a new vector for it after self-attention, let's say. It turns out the whole point of self-attention is that when I create this vector, I should rely on appropriate other words to influence the new vector. Okay, and you can see that it perhaps corresponds to the animal, and so the animal's vectors, the and the animal vectors are kind of heavily influencing the it vector. Okay, it's very similar to the encoder-decoder thing with LSTMs, but it's just showing that what attention is supposed to achieve. It's supposed to kind of, when I'm trying to transform the vectors related to each word, I want to see what else is supposed to influence the current word's vector representations. Okay. So let's actually now come back to thinking machines illustration. So what we're going to do is see how this influence happens. Okay? This attention mechanism computation is going to be very similar to the encoder-decoder attention mechanism that we saw a few minutes ago. So yeah, so we'll start. So now we're going to look at computation. It's happening from top to bottom. So each step just says what is the computation happening. So the input is this words. We're at the first encoder unit, and let's say we have the embeddings for each of the word x1 and x2. Okay, from this word, we're going to create 3 new vectors. Okay, per vector. So per green vector, we're going to create 3 new vectors, and we'll ascribe specific names to them. It's called, the first one is going to be called a query vector. Second one is going to be called a key vector, and the third one is going to be called a value vector. Okay, how did we get these vectors? A very simple multiplication with a matrix. It's a parameter for the self-attention block, WQ, WK, and WV. Okay, so what am I doing? I'm taking x1, multiplying it with WQ to get Q1. I'm taking x2, multiply with wq to get q2. Okay, so similarly, wk and wv. Okay, so I'm getting 3 vectors per vector. Okay, that's the self-attention, one of the computations in self-attention. Once you have these 3 vectors, we'll do the following, which is we have these 3 vectors, so just same picture as before. Now what we want to do is go from x1 to z1. Remember, x1 produces z1, x2 produces z2, but we just want an influence from the neighborhood. In this case, there's only one other word, so we'll see how the influence happens. So what we're going to do is first multiply query vector with every key vector. So in our example, there are only 2 words, there are only 2 keys. Okay, so we focused on going from x1 to z1, the output of the self-attention, and we have a q1, the query vector, that we're going to multiply with its key vector and also the neighbor other word key vectors. Okay, so I'm going to multiply q1 with k1, and I'm also going to multiply q1 with k2. Okay, so just multiplying the query vector with the other key vectors. Okay, what is the purpose of this? This is kind of mimicking trying to get attention weights, basically. So these queries and keys are trying to give a sense of, remember last time, how did we get attention weights? We just said, okay, some inner product, and that's gonna give my attention weight between the encoder and decoder hidden vectors, right? Similarly here, there's no notion of encoder and decoder yet. I mean, it's because we are still at the level of like going within the encoder unit, just going from x1 and x2 to z1 and z2. So all we are trying to do is use the query and keys to produce attention weights. Okay, so right now we have produced not exactly attention weights, but let's call it attention scores, which just depend on query and each of the keys. Okay, so if there were 3 words, there will be q1 times k3 as well. One more if there were 3 words. Okay, so some numbers, 112 and 96. And then what do we do? At least in the original paper, they did some scaling operation. We'll not really get into the, why the scaling is needed, by just some division by some constant, essentially. Okay. After that, exactly the softmax operation that we've seen. So you have 112 and 96. Just do e to the power 112 divided by e to the power 112 plus e to the power 96. You get a couple of numbers, right? So that's 88 and 12 by 100. So 0.88 and 0.12 once you do a softmax operation on 112, 96. Okay, so that's now what we got here is literally attention weights. The only vectors that we have not yet used are the value vectors, v1 and v2, right? So what we're going to do is just use these weights to do a weighted average of v1 and v2, and that weighted average we're going to call it as z1. Okay, and then we'll repeat the same type of processing, except q2 will be used to with key1 and key2. Sorry, key1 and key2, and then appropriately do a weighted averaging of the exact same values to get now z2 as well. Okay. So what I mean, so softmax times value and then and summation, right? So it's a weighted averaging to get z1. So that's how we go from x1 to z1. So you are relying on neighborhood effect by using the other words keys on the other words values to influence your output. Okay, obviously you're using your own words, keys and values as well so your current word also is influenced by your current words values and so on, but is also influenced by other words. Okay, so this is the effect that the self-attention achieves. Okay, mechanically what's happening, and obviously intentionally, like what is the intention here is to really have this cross word information propagation, so that if there's a word like it should refer to the animal. It can rely on such information to kind of have better representation for these words. Right? Any questions here? Yeah.
So in terms of when we have this sense, it's always going to be like this instance machines that we think. So is it always going to use the query term from the previous word for like those Q1 times Q2? So if it was longer, would it be like Q2 times K3 and then so on and so forth?
Yeah, if there are 3 words for attending for just so we are only focused on generating Z1 in this illustration so far. For Z1, yeah, if there's a 3rd word, there'll be Q1 times K3. There's a fourth word, there's Q1 times K4. Appropriate four softmax terms will be there, and then a 4-term weighted average will happen. Now, let's say we are focused on the second word. We're going to go from X2 to Z2. Then it'll be Q2 times K1, Q2 times K2, Q2 times K3. Yeah. So queries for each word are the ones which are kind of determining kind of how to work with keys to produce some weights, which can be used for weighted averaging of the values. Okay. Yeah. So the role of queries, keys, and the values is kind of there's some database language being used here, like keys and values, key value stores. I don't know if you've heard of perhaps. Queries are like if you're doing nearest neighbor search, then there's a query, there's a what points are close by. So these are just names that were co-opted and kind of to define like what is the operation going on here. Okay. So nothing. I mean, operationally is just a bunch of inner products to get attention weights essentially, and then doing a weighted averaging of the values. And how did we get these three vectors? They're just transformations of the input vector, like linear transformation. So it's just applying a linear layer if you want to think of it that way. Okay, so to kind of remark one more thing is that so the self-attention block has literally those parameters, the parameters that determine the how to compute the queries, keys, and values from the inputs. Those are the parameters for each self-attention block will have those three matrices as the parameters. Okay. Okay, so here is the same thing, except now in a vectorized, I guess vectorized or matricized version. We're just saying, okay, if we had two words, then that times that these are the parameters, as I said, WQ, WK, and WV, to get the query matrix, key matrix, and value matrix. And just a vectorized version of what we just discussed. And the computation of Z can actually be again shown in a vectorized way, where you just take Q times K transpose. This is a matrix multiplication, which GPUs are very efficient at. Some scaling, and then softmax operation element wise, and then apply a multiply that with B. Okay, so it's just a bunch of matrix multiplications going on. Okay, so this is not the complete self-attention story. This is the core block. Now all we're going to do is add some redundancy. Okay, so that's what we'll see next. Okay, add some redundancy in the self-attention block itself, and that's the notion of multi-headed attention. Okay, the idea is very simple. Okay, we got the X vector, and from which we created the Z1 vector, X1 to Z1 and X2 to Z2. And while doing so, we created only three vectors, which is a query, key, and value, and query, key, and value. But why just create one set? Why not we create 8 of them? Why not we create 16 of them? Okay, what do I mean by that? So for the same input, why don't we use multiple WQ, WK, and WV matrices and produce multiple queries, keys, and values? They don't interact across each other, but you do the same computation multiple times. Okay. So basically doing multiple this attention computations that we saw in the previous couple of slides in parallel. And in this illustration, we're just showing that. So let's call it attention head is just the name for that computation step happening. So it's just a, inside the self-attention, there's an attention head. Attention head just corresponds to this one set of these W matrices. Attention head number, let's say number 1 corresponds to one set of matrices. Attention head 2 perhaps corresponds to another set of matrices, and so on. But each one, at the end of the day, will produce a Z vector. So it's just parallel computation. The only difference is that these three matrices, the only difference would be that perhaps they are initialized differently in the model. Okay, when the model is getting trained. Okay. So how does it help? It's basically redundancy. So perhaps it should focus on both the animal and some other location, some other word. Then perhaps the first attention head lets you focus on the word animal. Maybe the second attention head helps you focus on some other part of the input sentence that is useful for this word. Okay, so so that's what, some redundancy, potentially different representations perhaps of the word that are appropriate for eventually, predicting or decoding, or in this case, like translating, right? So that's the idea. And so generally, I mean, there's going to be in the actual pre-trained models, there's a specific number of multiple heads that they use to define the self-attention block. But in this illustration, we're just saying, okay, if there's X matrix, one row per word, then there's going to be obviously Z0, Z1 to Z7. If we have 8 attention heads, we just saw how to go from X to Z0. That was the initial operation. We just made a copies of it by saying, okay, there could be multiple such W matrices, multiple attention computations. And what do you do? So now you have like much too many outputs. What you can do is just average them out, for example, or instead of averaging, if you want to do a little bit more sophisticated computation, you just concatenate them, Z0, Z1, Z2, Z3, Z4, and then multiply with another parameter. Now, this is also going to be now a parameter of the self-attention block, which is just going to reduce it back to the appropriate dimension that you care about. For example, if the input vector was 4-dimensional, although these Z's are 3-dimensional, you can say I want to go back to 4-dimensional by just having a appropriate matrix here. Okay. So it's just saying if you do multiple head computation, you can concatenate those vectors and project it down to appropriate dimension that you care about for passing it to the next encoder unit. Okay. Any questions here? So this is just a kind of say what are the parameters of this self-attention block and what is the computation that's going on. The computation is all about how can I use other words information to influence my word representation every step. Okay. Okay, so this is just summarizing what we just talked about, going from either at the first encoder layer, there's going to be the actual word embeddings, but if it's not, it's going to be some other vectors, input vectors. If there are 8 attention heads, those many matrices will be there. Those many queries, keys, and value matrices will be there, and each one produces an appropriate Z matrix, and then you can apply an aggregation operation through concatenate and then multiply so that you can get back to the 4-dimensional vector you care about. Now these Z's will become R's for the next encoder unit, and so on. So you could have like 6 encoder units, then each encoder unit is basically doing this, where the parameters are this and W0. Okay, those many, so a lot of parameters, actually, so many matrices, but they're not too big. Okay, so why are they not too big? Is because although X could be, let's say, 512-dimensional, 300-dimensional, whatever is the embedding size, the queries, keys, and values generally are chosen to be a little bit smaller, like 64 dimensions or 128 dimensions or something like that. Okay, so they're still big in terms of, they're still big matrices, but not like huge. Okay, so here is an example of looking at 2 attention heads. Okay, so where are the 2 attention heads? Because you can see color gradient in one color here, and then right next to it, another color gradient with another green color here, right? So it's the same word, the it word that we saw with single attention, like when we were looking at a few slides ago. But now you can see that for one attention head, while thinking of computing the it word, like transforming it and looking at which other words, how their value vectors influence. And for the one of the attention heads, these words seem to be important. The animal didn't. And then for the second attention head, looks like too tired was actually was trying to influence the representation of that word. Okay, the values for those words are being, I guess, highly weighted. This is just a visualization tool. Again, these types of attention mechanisms, whether it's encoder decoder attention or self-attention, once you've already trained the model, you can always pick a canonical or some sort of a prototype pair of data points and then see how the attention is working to get a better intuition for whether attention is actually useful or is able to explain something that you found interesting in that data pair. Okay, but it's not always so rosy. It turns out it's very hard the moment. So here we're just focusing on 2 attention heads. The moment you have 8 attention heads, there's going to be so many other color combinations that you'll see. Okay, and so it's going to become very, very messy, right? So for example, here is the full picture where you have 1, 2, 3, 5, 6. Okay, so all the 8 attention weights are being shown. or basically the query times keys values, basically the intensity, that's what it represents. And here it's like, looks like the word it has influenced by every other word, which is not really very helpful, right? It's saying it is being influenced by because in the last attention head, and in the second attention head, it's being influenced by the animal. And so it's not really very explanative. Okay. But this redundancy, this multiple representation, this parallelization seems to help really well. And that's why it's become a canonical choice in many of the transformer-based architectures, whether it's translation, whether it's LLMs, whatever it is, generally they go for multi-headed attention. Okay. Okay. Let's take a break for 10 minutes, and then we'll get into the next few additional remarks or details on this attention business. Okay. Yeah, before I continue where we left off, we just talked about multi-headed attention. So all that material is actually from this extremely famous paper called Attention is All You Need. Actually, let's actually search on Google. Let's look at this. Yeah, it has 110,000 citations, which is a lot, given the number of researchers here. But yeah, this is the paper that we are discussing actually. So if you look at the, click on the PDF, and this is, by the way, already, there's also linked on the, our lecture goals page has a bunch of links, and one of the links is this one. So Google has some requests for using figures and stuff. But if you look at the figure here, this is what we're discussing. Okay, so we'll probably come back to this if needed at a later point. So far, what we've done is just look at the this orange block here. So we'll talk about the remaining stuff in a second, and also talk about decoder and stuff. So we'll talk about the rest of the architecture in the next hour. Okay, so we can go slow. We don't have to cover all the 100+ slides that are there, but this is what we are trying to slowly understand. And actually, this figure is also there in the link called, which is also on tutorial site on PyTorch. It's exactly the same figure. They reproduce it. I don't know, with attribution. I'm sure with attribution, but it's the same figure. And I don't think this figure is there in our slides, but it is a figure from the paper describing the original attention architecture. So we'll look at this, but there's also another link on the course page. This person has great summaries on various different topics in machine learning. One of them is related to attention, and they have added, and they also probably use the same illustration at some point. So we have seen this illustration. Let's see if they use the same illustration, but yeah, so this is from that paper. So this is again a link on our course lecture links. So you can also look at it. It relates to not just this type of attention, not just the encoder decoder attention, but all other types of attention that, not all other, but like a good chunk of attention related concepts that people have invented in this, in the machine learning domain. You can see, I think there was a table of contents. There is a table of contents. So self-attention, some other type of attention called soft and hard, global and local, multi-headed encoder, decoder, a lot of details. Okay, so if you want to further study and really get into this area, then this is a good point. So I want to come back to two things. One, I want to visit this for a second, because we'll actually see this perhaps again. This is a nice visualization tool, just very similar to the LSTM Viz, I think, the tool that we were seeing with the attention weights. So this is just showing how the tokenization is happening for different models. Okay. So although you guys wrote a tokenizer, or we had a tokenizer in the illustrative example also for assignment 3, right? So you were able to parse the IMDb data and get the, basically tokenization is essentially converting words to indices, right? So the encoding step is just getting indices, and so you're also maintaining indices to what were the words corresponding to it, right? So here for GPT-2, which is based on the transformer architecture, they also need tokens, right? So they also need to know what is the word unit for which we're gonna get an embedding. So you can already see that they're actually not at the word level anymore. So you can see, for example, this is a sentence I got from our slide, the slide we're gonna look at. And you can see that many of the tokens are actually word level, but in this word, you can see disambiguating. This is a token. It has 6,381 as the token index. Similarly, amb is a token. IG is a token, awaiting is a token. So it's not always the full word which is a token, is what I want to show, right? And it has some 27 tokens for this sentence, and depending on different architecture. So I guess GPT-4, let's try GPT-4. It has 16 tokens, right? For the same, oh no, not the same. The example changed. I was like, why? How can it be like this? But yeah. I guess GPT-4 has a different architecture. Let's focus on GPT-2, which would be the closer architecture to ours. I lost the example, but just trying to show that this is a good visualizer to look at how does tokenization change as a function of the model architecture also. In the sense that when people built these models, they didn't stick to a single way to the way we did it for IMDb data. They didn't like literally write a index a dictionary which goes from words to indices and indices to words, which is what the vocab object is. They didn't just write it like naively. There's like an innovation on the tokenization aspect as well, because otherwise you can end up with character level models or just word level models. They're not very flexible. So there's something in between that people have figured out is the right way to go. Okay. And then all these models now, at least the proprietary ones, they're all charged by number of tokens. So it's good to kind of get a sense of what are the tokens and how are they influencing things. Yeah. So anyway, we can come back to that and that figure in this paper in a second. But before that, as I said, in the paper, we only looked at this orange block so far. And we want to kind of just fill up the rest of the things, which are actually pretty straightforward. That was the self-attention is the new thing. Everything else is a little bit, we have seen it before. So first idea, which we've not seen before, but it is a little bit, does give you a sense of why it might be needed, is the idea of positional encoding. Okay. So far in the self-attention step, and therefore in the encoder unit in general, there's no notion of which word precedes the other. Okay? The order doesn't matter, because if I'm looking at one word's transformation, let's say Z, X10 to Z10, whether there's previous 9 words or whether it's subsequent, let's say 5 words, whether you flip them, it doesn't matter, because every query, so my query, I'm going to multiply with each one of the keys. Okay, whether those keys are 9 to the left and 5 to the right, or whether it's 5 to the right and 9 to the left, doesn't matter. Okay, I'm just gonna do a weighted averaging of their values and just get my Z, right? So it doesn't matter, the order doesn't matter. So in some applications, it's okay to not worry about the order, but in some applications it is useful, especially in sentences, natural language processing. So the idea is to encode positional information. What is the naivest way to encode positional information? Perhaps you can just add an extra coordinate to your word vector and say, hey, this is position 1, position 2, position 3. You can do that. But that's not considered a good way to encode position. There are some other, I would say, seemingly non-intuitive ways, but they seem to be good. They work very well. So one of the ideas is basically have these pre-generated vectors, which are here represented as T1, T2, and T3. These vectors are pre-generated, predefined. There's just programmatic deterministic way of defining them. And these vectors are added element-wise to X1, X2, X3. And then that final, that transformed X1, X2, X3 are the ones which are passed in to the network. Okay. So you may say, okay, if I'm adding some arbitrary predefined vectors, they're just shifting my word information arbitrarily. That is true in one view, but it's the other view is that this actually captures that x1 precedes x2 precedes x3. Okay, this does. Okay, and why is that? Because t1 and t2 and t3, they are position dependent vectors. In a sense, is the same t1 in the next for another example also. So it's invariant across examples as long as it's in the same position, right? So what are some of these examples? You can see one, and this is kind of illustrative but kind of realistic also. So here's an encoding, right? 0011, and then some other encoding where it's going down and going up. So 0.8 to some low value, again back to 1, and some variations. Okay, so here I think it's not very clear, but you can see in this pattern, this is a pattern from a somewhat some architecture called transformer to transformer. It's okay, it's some architecture with some extra bells and whistles, but the core part is you have to kind of encode positions, and there they used these vectors. Okay, what is this? It looks like a matrix, but each row corresponds to a positional encoding vector. Okay, each row is a 512 dimensional vector, so the x-axis is basically it's the columns. So each row is the positional encoding. So t0 would be this long vector, and here you can see what this vector is. So this color probably means zeros, and yellow means ones. So a bunch of zeros followed by a bunch of ones is encoding that you're in the first position. Okay, whereas the last vector has, it's going between minus values to some ones and minus values to ones, and so on. So it's jumping around, right? So that corresponds to the last vector that you can last position that you can have. So in this transformer architecture, there's only 20 is the length, max length of the sentence that you can process. Context length is what it's called, and so that's why there are only 20 position encoding vectors. Okay, these are predetermined. How are they defined? It's just some function, some cosine or sine function of numbers to get these values. Here's another positional encoding, which is only 64 dimensions in length, 64, which is the number of columns here, and the number of rows here is 10. Okay, so it's just an illustration of how positional encoding could look like. So here is an example where the 0th position means 0, 1, 0, 1, 0, 1, 0, 1, and so on here. So when you add this to x vector, you can see that coordinates get changed quite a bit. But still, this is it turns out that this is a good way to encode position in your data. Okay, any questions here? No. Okay, so positional encoding is one thing that we need to capture, because the original canonical encoder block or the self-attention subblock that we talked about, sublayer that we talked about, doesn't have a way to kind of capture position. Okay, as I said, naively you can just add a position value if you want, but that doesn't work as well as the methods that we just saw. That's on the position side. The rest of the encoder block is a little bit straightforward, but has some tricks or some ideas in there. So this is the rest of the encoder block. So what we've spent so far before the break is only this yellow, this orange block, right? Self-attention. So what else is there, right? So each sublayer has residual connections that skip it. So what is the sublayer? The self-attention is a sublayer. The feed forward is also sublayer. Remember, those are the two sublayers in my encoder unit when I was showing it illustratively earlier. So they also have residual skip connections. They have residual skip connections, and there is also a normalization step, which is shown in green here, that also happens. Two things, right? So what is residual connection? That's already shown here. So so at any given point, right, it doesn't have to be at the bottom, but any given point I have a vector, whether I'm getting into a self-attention sublayer or a feed-forward sublayer, the same vector also skips that layer and is added back at the output. Okay, so remember, you have used ResNet. We didn't see explicitly the ResNet architecture. ResNet architecture is a very similar idea. You go through a con layer, but you also skip the con layer, and both tensors get somehow concatenated and then passed forward. It's not that, essentially that's the core rough idea for ResNet. Okay, to have residual networks or residual connections. Here is the same idea. So you pass through the feed-forward network, for example, and also skip it. But obviously, after skipping it, you have to aggregate both the processed one and the unprocessed one. Same thing with self-attention. So you pass through self-attention and you skip it, and you have to somehow the processed one as well as the unprocessed one you have to add together. And here it also says normalize. Okay, So that's the one new thing, which is skip connection. Okay. Second thing is normalization. So let's zoom in on the normalization step, which is this add and normalize block that we saw from the previous slide. So what is happening, right? So here we are applying what is called a layer norm. So we have seen bash norm 3 lectures or in lecture 3 or something, right? So here there's a slightly different normalization step called layer norm. And what is layer norm, we'll see in a second, but basically we have X which went through the self-attention and also X which did not go through the self-attention. X which went through self-attention got a Z1, Z2. Let's put them one on top of the other. That's this pink color here. Things that we did not go through self-attention, we just put it on top of each other, and that's the X here. Okay. So what is layer norm? Layer norm is basically the opposite of batch norm. Batch norm is looking at across batch neuronal outputs. For the same neuron, across batch, some numbers are produced, and we just do a kind of a take the mean, subtract the mean, and divide by the variance. Okay, that's across the batch operation. That's why there's a batch norm operation, batch norm in the name. Here, we don't care about the batch. We just focus on the current, for this current input-output pair. Let's say we are doing translation. We just have the current couple of words. And so we just want to normalize each, we want to normalize each vector. So x1 and x2, we want to subtract the mean and divide by the variance. Okay, it's just the vector level averaging that's happening. Okay, so this is actually from a paper called layer normalization, and I don't know if you recognize some names. So this person, the last author, has a huge contribution, has been awarded a top prize in computer science for this work. Not just layer normalization, but in general for deep neural networks. I think was also the contributor for AlexNet. In fact, AlexNet was from his lab. His student built it, which did that ImageNet improvement in lecture 1, right? So they wrote this paper in 2016, and it's a very simple idea, just the mean and variance to normalize these vectors. So once you add x1 with z1, you get a bunch of numbers. I just want to subtract the mean and divide by the variance. Okay, so it's very different from batch norm, but it's a very simple idea, but kind of helps with the stability of the whole end-to-end training backpropagation. Okay. Yeah, so that's layer norm. So far, what have we seen? Positional encoding, residual connections, and layer norm. Okay, so 3 things. So what's left is to just briefly talk about decoder. I mean, we're also talking about residual connections, as the heading says here. But residual connections we've already talked about. I don't know if we're talking. Yeah, we're going to talk about decoder. Okay, so this figure is basically showing you a very in gory detail that there are 2 encoders in this illustration instead of the 6 in our 10 slides ago, and 1 decoder, with the second decoder just not shown here fully. Okay, so now you can see visually like how many blocks are there. This feedforward, it looks like there are 2 feedforward layers. It's not really layers, right? So each word will have a W, B. Each encoder will have a feedforward sublayer, and there will be a W, B parameter there, and that will be used for every word. The same W, B parameter will be used for every word. Okay, so this feedforward is just a transformation of the whatever layer norm output. Same thing, this feedforward is a transformation of layer norm output, but these also have their own residual skip and layer norm operation going on. So skip connections help with, in case there is a dead ReLU and all that, there is a way to propagate information forward and backward. Any questions about this? What we have not talked about is what is this extra encoder decoder connection attention in the decoder block, because decoder block looks exactly the same, right? So it's basically exactly the same skip connections, self-attention, add and normalize, except there is an extra encoder decoder and add and normalize in between. Okay, if you think of that step as like an identity function, then it's exactly the same as encoder side, right? So the encoder decoder attention is precisely because if I have an input of length 5, let's say five words, or input of length 2 words, or input of length 20 words, I would have produced 20 vectors at the end of this encoding process. Okay, those 20 vectors, it's exactly not vectors, but we'll also have queries, keys, and values. But let's say it was a vector, then that kind of, they look like 20 hidden vectors from our encoder decoder attention discussion, right? If you're doing an RNN based encoder decoder attention, there would be 20 hidden vectors, and every time you're trying to decode, you kind of rely on, oh, which of the 20 hidden vectors on the encoder side would be useful for current decoding. It's a very similar idea. If we have 20 vectors, if or 2 vectors or 5 vectors, depending on sentence length, then you kind of have to attend to those vectors while decoding the first word, while decoding the second word, and so on. Okay, that's the idea. Any questions here before we get into a little bit more detail about the decoder? Yeah.
So within the encoder, the feed-forward layers are the same. But
yeah.
Across the encoders, they're different.
Yeah. So the weights. So yeah. So this feed-forward layer here and this feed-forward layer here will have different weights, but these two in the same row will have the same same parameters. Same thing. This self-attention here will have a bunch of weight matrices to produce the queries, keys, and values, and also to aggregate if it's a multi-headed attention setup. And those weights will be different from these weights. Unlike an RNN case where it's the same parameter being applied across the sentence length, because it's a different paradigm altogether. Okay, so let's talk about encoder decoder attention. I will not get into too much details of encoder decoder attention because we already talked about it. But let's see, at least in terms of decoding wise, how does it work, right? So as I said, on the encoder side, so here's a picture just to kind of get a sense of how decoder works without getting into too much details of like the decoder's internal workings. Is the following, right? So the output of the top encoder unit, let's say in this case, there are only 2 encoder units. So the top encoder units, there'll be 3 vectors, right? Typically, there'll be 3 vectors. Let's call it R1, R2, R3. Instead, we'll think of not just 3 vectors, but 3 vectors with transformations very similar to the queries and keys and values that we did. Here, we'll just focus on generating keys and values. Okay, so what we're getting is for every word we get 1 vector, but we'll just make that 1 vector into 2 vectors. So by how do we make it into 2 vectors? We just do two linear transformations basically. So that way we get to the encoder these keys and these value matrices. There are 2 rows because there are 2 words. I'm trying to see why there's a 2 here. The 3 words. Interesting. So, okay. I don't think I'm able to explain the dimensionality correctly here, but so for 3 words, all I'm trying to say is that if there are 3 words, there's going to be 3 keys and 3 values. Okay, let's not worry about the matrix form of it. Just think of it as a single key, 1 key per word and 1 value per word. Okay, because duplication is just to do with duplication is just to do with additional parallel computation. Okay, which we don't want to get into for now. So we get these keys and values, 1 per word, right? And we're going to use all of them together once, they're all generated once we go through the encoding process. We're going to use all of them together while decoding. Okay, so that's how the information is passed from encoder decoder stage here. Okay, so at time step 1, we already have these vectors, these keys and values, and we want to generate the first output. Let's say the first output is I. I don't know if I have the details here. Okay, I don't have the detailed opening. So So while producing the I output, you can think of starting with a start token or something like that that's not being shown here. For example, here, right, when I'm producing the first word output here, I'll start with some default token, or which is not being shown here. Decoder works sequentially, just like you did it in your assignment also, or in the encoder decoder machine translation setup, right? So how do we do the decoder in a sequential way? We're gonna use this. We're gonna do exactly as before. In each decoder unit, we're gonna first pass through a self-attention layer. At this point, our input is just the start token and nothing else. Okay, so it's like a sentence of length 1. So there's really no attention to be done, really, because there's nothing else to do. That start token is going to create a query, basically query vector. That query vector is going to get multiplied with these 3 keys to produce 3 attention weights, and those attention weights are used to do a weighted averaging of the values across these 3 values, because there are 3 words here, and that value is then that weighted average is passed through the feedforward layer. So if you see this, all I'm saying is there's here, although here it shows that there are 2 words, but let's say the second word is we're doing the first decoding. The first attention, there's no self-attention happening essentially, because there's no second word. That one, when you get to the encoder decoder step, that's where the keys and values from the encoder side are used. Your output is going to work as a query. So query times keys is going to produce a weighted averaging. So it's going to produce attention weights. And then you use those attention weights to do a weighted averaging of values. And that's the thing that is passed up. Okay, that's how you use that's why it's called an encoder decoder attention step here. Okay. And then the rest of it is the same. So at the very beginning, you don't have anything else to decode. So it's a very straightforward, like linear transformation, add a normalized transform. And then you get a linear layer to transform back to the distribution over vocabulary size. And then you get the scores, you do a softmax, and you get a distribution over vocabulary, right? Now, once you produce the first output, like taking the max, the word with the highest probability, let's say that's I, then you feed that I back down, right? So that will be your start token, and now you have your first word. Okay, now you have a 2 sentence length input. Then you pass them. Now there could be some attention things happening, but exactly the same operation. So at some intermediate point, the vectors being passed from the self-attention block will become queries only, and then everything else that's being passed from the encoder side will be encoding process would be the keys and the values. And so exactly some weighted averaging happens, and then those vectors get passed up. Okay, so this happens sequentially. And as I said, the only thing to note is that because it's happening sequentially, at any given point of time, if I have decoded 3 words out of potentially 6 words, then decoders, just like encoders, they have fixed number of max words that they can process, like 20 or something. And so the remaining locations are all basically zeros. They're not really active. Okay, that's how you do it. So because the remaining locations are basically zeros, they don't contribute to any attention weights or any transformations or anything like that. Okay, so that's how it's as if they're not, they're not there, and that's the right way to do it. Think about it, because you're sequentially generating 1 word at a time. So you can only look at the left side. So if you're decoding the 4th word, you can look at the left side, which is the first 3 words, like I am. You can look at I am to produce an A, but there's nothing to look at the right side because they're all zeros. Okay. Any questions here for encoding or decoding? Sorry. Okay, so at some point, you pass in the appropriate number of words, and hopefully your highest probability thing is an end of sentence or some special token, and you stop there. Okay, which is the same as any other variable and output generation process. Okay, so this was pretty much the hardest part of the whole operation. So we literally just went from just looking at the orange block before the break to really cover everything else in the past 15 minutes or so in the right now. So this figure from the paper is just showing the input embedding, the positional encoding. Input embedding, kind of element-wise addition of positional encoding, which is predetermined. And that's why the symbol is some sort of a sinusoid, because they're predetermined, maybe cos function or sine function or something, every location. And then you have multi-headed retention, the skip connections, which you do additional normalization, with layer norm, a feed forward layer, which is every vector there is, if there are 3 vectors, 3 words, and 3 times the linear transformation, whatnot. And that's one encoder layer, one encoder unit. And you could have many of them. And we'll see later some examples, like BERT has 6 and 12 encoder layers, or maybe even 24. I'll have to look at it. And then on the decoder side, it seems like a much bigger block, but the only thing that's adding is this encoder decoder attention that's happening. And the second thing that's happening is what they call as masked multi-headed addition. Masking just means that, as remember, we have to decode one word at a time. So, which means that the right-hand side influence should not be there, whereas there should be left-hand side influence. Unlike the encoder side, whereas we know all the words beforehand, so we're just getting influenced by both the words on the left side and the right side. Here, there's no influence from the right side, right? Because we are creating one word at a time. So that's what we need to just account for appropriately. And that's why you can see that this encoder decoder attention, that block, the keys and values are fed in from the encoder side, and then from the bottom side, we're getting the queries. And so with the 3 inputs, we are just again following the same conventions. Okay. So if it's not clear what this diagram is, you can go back to our illustration and just kind of map it. And if you're still confused, you can always reach out to me. Okay, so we've kind of crossed the hardest path here. Now it's just going to be some remarks and simpler things that you've already seen. And so one of the aspects is once you get the decoded output, the next 2 steps are just linear transformation and softmax operation, which is something that we've seen like millions of times so far. So by now, so linear transformation just produces a bunch of scores. Softmax transformation produces a bunch of probabilities, and you can take the log probability of the true index, right? So when you're doing training, you look at, true index should be M for that second decoded word, and whatever its index is, and what's the probability for that, and that's the negative log probability that you want to kind of minimize, or the log probability or probability is what you want to maximize, right? So that's just by definition. So here we're just talking about the exact process that you went through in assignment 3, which is going from words to indices, indices to words. And the whole concept of doing this tokenization is itself an interesting topic, especially with large language models, where different models have different amounts of tokenization. So some models have 1 million tokens. Some models have, hundreds of thousands of tokens. Some models have much lesser than it, right? So this choice, you could go at the character level, which has its own limitations, and you can go at the word level, which has its own limitations. And in between is what the situation is today in 2024, 2023. This is just showing what is the, if you have an index, then your target will be one hot encoded, which to pick up the appropriate coordinate. Like you will produce a distribution of probabilities, and if your target word is am, then whatever the location of am is, that's the word that you want to pick up, right? So you can just think in terms of one hot encoded element-wise multiplication of log probabilities, where if everything else is 0, then those log probabilities don't affect anything, and this log probability related to am is the one you want to maximize, or negative log probability you want to minimize. So I'm not explaining anything new here. It's just cross-entropy definition, which is that if you had these type of probabilities, then if you want to pick thanks as a word and you want to maximize its probability, then it's just element-wise multiplication. So that's why the word cross-entropy comes. I know we have not spent much time on the word cross-entropy. If you remember, entropy is by definition is the negative sum of the probability times log of probabilities, right? If you look at the definition of entropy, if you look up Wikipedia, it's just a negative sum of the pi times log pi. If you drop the pi to something else like qi, then it's called cross entropy. In particular, the qi, if you make it 0, 0, 0, 1, 0, 0, it's still a probability mass function. It's a very degenerate probability mass function, which means that it basically what it does is drop the summation and says, okay, only look at the probability corresponding to the true word, corresponding to the true label, right? That's why we have, for every example, we have a minus log of the probability of the true label, right? That's why it's called cross entropy. Okay. Yeah, this is just showing the same thing. So we'll skip this slide. Yeah. Basically, it's picking up the appropriate probabilities and seeing if they're high enough or not. Any questions here so far? Okay, so next 10, 15 minutes, what we're going to do is just go from that idea of static embeddings, the word-to-vec, low, fast text, whatever, to these dynamic embedding example, or dynamic as in like contextual embedding example, which is basically another way to say we're going to see how to use pre-trained NLP models. We have not seen, so we've seen use of pre-trained vision models, like you've used ResNet 18 and whatnot in your assignment, but we have not seen like a full equivalent of ResNet 18 here. We've only seen like word embeddings, right? So it's like literally dictionary lookup. It's not really a model. There is no neural network that you're reusing again and again. So here we're gonna kind of see that through an application. What application? We're gonna look at the simplest application, sentence classification. Okay. So let's do that. We're going to basically look at the application of sentence classification and the idea of transfer learning or the idea of transfer learning for NLP models. For that, the model that we're going to look at is called BERT. Okay, so BERT is the way we're going to use BERT here is as a pre-trained NLP model, word representation model, basically. And as I said before, we have seen word-to-vec and GLOW in assignment 3 already. What's new is the use of transformer-based pre-trained models. BERT is one of them. BERT stands for bidirectional encoder representations from transformers, but it's basically representations of words. Okay, bidirectional means that words on the left to it and right to it are together influencing its representation. Okay, and so we'll look at one of these models. Distilled BERT is like a small version of a distilled version, some reduced version of the BERT model. Okay, there's this notion of distillation in machine learning in general. Distillation just corresponds to if you have a very complex model, much bigger model, let's say a 10-layer neural network, you can say, okay, I can use a 10-layer neural network as like a reference network and use that network's outputs to kind of generate data, which can be used to train a much smaller model. Okay, that's like that's called knowledge distillation. You're going from a 10-layer network to maybe a 3-layer network. So that's called distillation in general. And there's also variations called data distillation and others. But that's what it means. Distill just means go, have a small version of some well-known or big complex model. Okay, so why are we talking about BERT is even in so several years ago it's already there, and today actually LLMs are part of search also, right? Bing has a LLM as part of its search. So BERT when it came about, about a year or two after the attention is all you need paper, in a couple of years, the company Google already included that as part of its search process. So it started using BERT embeddings to kind of understand what is the encoding of the keywords that people are querying. Okay, so let's, that's the context, historical context. The specific application we're going to look at is something that is like a review, which is just sentence classification. Okay, so what we're going to do is, what is the problem? Have a sentence, we want to label it as positive or negative. Okay, and our training data already has sentences and labels. Okay, this is exactly like the IMDb data set that many of you have already worked with. So while doing this, we're going to use this pre-trained embedding. Okay, it's going to be very similar, and so it's just, hopefully it's not too boring, but it's also not complex anymore. So I know we looked at some complex architecture details just a few minutes ago. So this hopefully is like a nice wind down to kind of reinforce that you can just use pre-trained models. So what we're going to do is exactly what we used to do with CNNs also. We have an input. We're going to use this distilled BERT or some pre-trained NLP model to kind of generate the appropriate embeddings of the sentence in particular, in our case, in this use case. And once we get the embedding of the sentence, just like we get an image embedding for the image, and then we can always do simple logic regression or something like that to make a prediction as positive or negative. Okay, that's what we're going to do. So instead of, the new thing here is basically that instead of thinking of embedding of each word, in the previous example, we've been pretty much in the context of translation. That's why we had an encoder and a decoder. If we didn't care about translation, we would just focus on encoding the words. Okay. Here we are basically on that aspect because of the we don't have to decode anything. We don't have a variable length output, so we are just focusing on the encoder side, which is what Distilbert will look like. And on top of that, we just want the encoding of the whole sentence, not just the individual words. Okay, so if you had the embeddings of individual words, you could do something, right? You can just average those perhaps, and then just say that's the embedding of the sentence. So you could do some naive things, but it turns out you don't need to do that for this pre-trained model. Okay, so what are we doing? So for each sentence, we just want to generate a embedding. And turns out for Distilbert, I think it's a 768 dimensional embedding, but that's all we want to create. So basically, our data set goes from words, comma, label to a vector, comma, label. Okay, it's just very, very intuitive, hopefully, at this point. So the way we're going to do it is that it turns out that the Distilbert model, there is a special token called the CLS token. It stands for classification. Okay, it's a special token, and the embedding of that token kind of literally reflects this embedding of the full sentence. Okay, so that's what we're gonna focus on. So it turns out that the Distilbert model, it's essentially a bunch of encoder units only. So there's no decoding because it turns out. And so on the encoding side, since it's a bunch of encoder layers, it just turns out that one of the tokens, which will pass, actually called the CLS token, it's the one, the embedding corresponding to it is the one which we'll use for downstream classification. Okay, so let's actually just zoom in on what that is. This is just a train test split, which I'm sure you've seen it for like 1,000 times, so we'll not look at it. But if you had the embeddings, you can just apply logic regression. This is just, again, steps that I don't want to cover, but this is like the next couple of steps. Let's come back to our embedding, right? So our tokenization step and what we need to do. So first of all, if we have the sentence here, a visually stunning rumination on love, then first of all, we need to do tokenization. And I've been telling you that tokenization is a non-trivial thing, and it's a modular thing and an interesting problem by itself. What is the level of tokenization you need to have? Is it the character level? Is it the word level, or somewhere in between? But it turns out that all these models generally come with their own tokenizers. So BERT model will have its own tokenizer. Distilbert will have probably the same tokenizer. But if you use some other model, it will have its own tokenizer. Generally, you can if you get these open source models, they'll tell you what the tokenizer you should use. So you tokenize, which is basically break the words into tokens. And tokens can be, as I said, it can be word, it could also be a subword. We just saw that with the visualizer earlier, right? And then what we do is add the extra tokens that help us use this pre-trained model for the classification task. Okay, so we'll kind of get into the details, a little bit of details of the BERT model later. What exactly? It's not about translation anymore. It's a pre-trained model that was trained for something, trained using some other auxiliary task, not exactly translation. But by training the auxiliary task, we learned some interesting good parameters, and that can be used for our current downstream application, right? So this is how you do it. So tokenize, and then add the special tokens, and then apply the word to index conversion. Okay, so this is the word to index conversion here, which CLS turns out for this model, it turns out to be 101, and a bunch of tokens, a bunch of indices depending on the token that you have. It's basically lookup. Yeah, so the way you do it is like something like tokenizer.encode, give you a sentence, and add special tokens is equal to true. Okay. If you did not care about classification, if you just wanted vector representation of words or vector representation of tokens, then you don't have to add these extra tokens, and you just get the vector representations of the word. Now, for example, if you focus on stunning, the vector representation of stunning really depend on other words in the other words present in that sentence. Okay, so stunning in this sentence would be different from stunning in a potentially different sentence. Okay, the vector representation. That's the difference from fast text and word2vec and glow to this pre-trained model. And yeah, once you have these tokens, this is how you would kind of when you instantiate a model. If you recall from your own model definitions, there will be an nn.embedding basically, right? So where you pass the tokens pick up the appropriate rows in the nn.embedding layer, and that's the one which are passed into once you do positional encoding, which all happens behind the scenes inside the model spec. They get processed through the embedded encoder layers, and then you get the embeddings. Okay, so yeah. As I said, it turns out for Distil-BERT and BERT model, there is the special token CLS is the one that we care about. So this vector here corresponding to this special word, is the one that we care about. And yeah, this closes the loop. So once you care about this word, then you basically do logic regression based on that word and the label, and appropriately get the label. Okay, that's all. So this is how you use a pre-trained network for this sentence classification task. Any questions here? Okay, so yeah, the rest of the process is pretty straightforward. But I want to just quickly recap the usage of the a pre-trained model. So transformers is a library that assumes if you already not yet used it, you should start using it, because it's one of the biggest hubs for pre-trained models. I mean, in the future there could be different hub, but this is the one from 2024 is a really good one. So the way you generally get a model from there is first you define what model you want, right? So here, Distil-BERT model, which tokenizer you want, Distil-BERT tokenizer, and which weights you want. Distil-BERT has some different types of weights, different variations in the weights, model weights. We want the base and uncased version. Okay, so this is just some extra suffixes for like, it turns out that the pre-trained models for the same model specification has different settings where you have a case, uncased, and case versions. Casing just means like a capital case versus lowercase. So you just pick the last one. So here we're just defining the 3 classes, and then from this class, 2 classes and a string, and we're going to create objects from those 2 classes. Okay? So for example, at the bottom, you can see that from the class, we pass the appropriate string and get the tokenizer object. And similarly, we can get the model object from the model class, again passing the appropriate string, so that we know what the tokenizers, what the right tokenizer is and what the right model is. These they come in combo like this. And if you have here I'm just showing a pandas kind of data frame. So if you have a column with a bunch of sentences, then you can just apply on that column. You can name the column if you want, but you can apply .apply operation. You can apply a function on every element of that column. And so we're just calling exactly the tokenizer.encode function. Okay, you might have done something like this in assignment 3, so it should not be new. And add special tokens is true because we care about the sentence level embedding that we want to use for sentence classification. Okay. I guess the only minor detail is about what is the output of the. So it turns out that this will be the maximum sentence length is 66. So if you have a sentence longer than 66, there's potentially an issue. You should probably truncate it or something. And obviously short sentences you should pad. I think padding is something that you've already seen for batching aspect. But here it's not so much about batching. I guess you can say it's batching if you want to pass everything together at the same time to get the embeddings. The only minor detail is about the model. When you call the Distil-BERT model and you want to focus on the first, only the vector corresponding to the CLS token, which is like the 0th vector or the 0th row, then you just have to do appropriate indexing. And the indexing is again tensor indexing. by which I mean indexing is something that you guys have been doing quite a bit in your assignment 3. So that type of indexing you have to do. So it turns out that the model generates basically generates like an output. It generates like one vector per location, right? So if it's 66 locations, then there's 66 vectors. So you only have to pick up the first vector or the 0th index vector, right? So that's the only detail. This step should be clear that you're just creating a tensor from a list by making it an array and then creating a tensor. And then with no grad, you don't care about gradients. Just doing an inference here. Okay. So the only thing, as I said, is that the last hidden states is the 0th element. You just have to pick the appropriate vector. So it's a 768 dimensional vector corresponding to only the 0th token rather than the 65th token. That's all. So you just have to pick these. Let's say this vector here, and then the bottom one you can't see, but let's say this vector here, right? So if there are 200 examples, then you just have to pick up the appropriate vector. So this is something. There's nothing deep going on. It's just appropriate indexing of your output tensor. Okay. Yeah. So I mean, yeah, I think these 2 slides just say something which is you guys are already familiar with, so I will not discuss it. Yeah, once you pick up those tensors, vectors corresponding to each sentence, then that's the embedding. And so you can just convert back to NumPy so that you can use it for scikit-learn or whatnot. Okay. Any questions here? I don't think I have anything else. Test range split, will not focus on it all. So any questions about this application? So the emphasis was just about there's a tokenizer, which is a pre-processing step, and there's the model. And Distilbert happens to be a good contextual embedding model where, depending on the context, the embedding changes. And although we didn't care about word-specific embeddings, we cared about having the special token CLS for classification, and that embedding corresponding to that or some vector representation for that would have information about the sentence so that you can just apply a simple classification once you have that. Okay. So this is a great way, right? You just literally short-circuited need for doing all sorts of sentence level manipulation or sentence level understanding by just using a pre-trained model. Yeah. You could have used word2vec here, except that once you do word2vec, you will have so many vectors depending on the number of words, and you have to do some sort of massaging them back into potentially a single vector by just averaging those vectors, for example, right? Otherwise, it's still variable length. Obviously, some examples that we've seen before, for example, with RNN lecture, RNN family, if you've done a word2vec, then you can just do a RNN step to create one vector by just applying the RNN block, so that if you have 10 length sentence, each of the vectors just can be condensed down to one vector, basically, right? Okay, so next couple of slides are more about what happened in the early years of this transformer architecture evolution, BERT and some other models. It's just to give a sense of tying it back with also the RNN models, which were also famous till 2020, 2021 perhaps, but they have a little bit become less popular given the predominance of the transformer-based architectures for some recent generation of applications. So the next few slides we'll cover in the next lecture. Okay. So if any questions, okay, if no questions, then we can perhaps stop here.